Okay, so a particular type of wave we're going to look at is electromagnetic waves. Now, electromagnetic waves are essentially a particular type of transverse wave. So if you remember transverse waves, we can represent like this diagram over here. And essentially, if you remember transverse waves, the oscillations are perpendicular to the direction of energy transfer. Now, electromagnetic waves in particular are waves that transfer energy. With electromagnetic waves, you will always have a source and then some kind of absorber that would absorb the energy from the source. Now, electromagnetic waves comes in all different types, and it's actually a continuous spectrum. So what do you mean by continuous? Well, a continuous spectrum basically means that there's no breaks in it. And so there will always be a point on the spectrum where you will find a wave, and there will be no gaps where there are no waves. Another thing to note about electromagnetic waves is they all obey the wave speed equation of V equals F lambda, and actually they all travel at the same speed. And that speed is the speed of light in a vacuum, so it's approximately 3 times 10 to the 8 meters per second. So they will all basically follow this speed, and that's the speed of all electromagnetic waves in a vacuum, and is approximately the same for their speed in air as well. And so we can actually take a look at the continuous spectrum of electromagnetic waves, and the way we look at this is we can group the waves depending on their wavelength and frequency. So if you remember previously, we said they obey the wave speed equation of V equals F lambda. And essentially, we can take a closer look at this. What this means is that if they all have the same speed, then essentially what we're saying is the frequency and the wavelength are indirectly proportional. So what that means is that when you increase the frequency, you'll have to decrease the wavelength for the same wave speed. And so what that means is that if we go to draw our spectrum over here, then if we say on this side, we're going to have our waves with a really high wavelength, and on this side are waves with a really low wavelength or longer wavelength and a shorter wavelength, then vice versa, your frequency on this side, on the left side, where the wavelength is very long, you'd have a very low frequency, and where the wavelength is a lot shorter, you'd have a higher frequency. Okay, and so now we can start to put some of our types of electromagnetic waves on. So the first one all the way on this side with the longest wavelength and the lowest frequency is going to be radio waves. So radio waves typically are used for communication. So one example of energy transfer is essentially when you might communicate over radio waves through a walkie-talkie, or when you play your radio, that energy is being transferred from the emitter to the source where you receive it, maybe on your radio or on the other walkie-talkie. The next one then, with the next longest wavelength and lowest frequency, is going to be microwaves. And so microwaves, I'm sure we're all familiar with. You can use microwaves to heat up your food, and so that's an example of energy being transferred from the microwave into your food to heat it up. The next one is infrared radiation. You can use heat-seeking cameras, and they're able to see infrared radiation, or a lot of the time if you have specific heaters, and they will emit infrared radiation. So again, it's another example of energy being transferred. The next one we'll do in yellow because that is visible light. And visible light is quite an interesting one because of all the electromagnetic waves on this whole spectrum, we can only see visible light. So we can only see a very limited part of the electromagnetic spectrum with our eyes. The next one after visible light is ultraviolet or UV rays, and these are the rays that are emitted from the sun. So sunlight contains a lot of UV rays. And after UV rays, you have your X-rays over here. So these are a shorter wavelength than UV rays but a higher frequency, and X-rays a lot of the time are used in medical imaging. So when you go to take a scan, maybe if you've broken a bone, a person will have a machine which will shoot out X-rays, and your bone essentially will absorb those X-rays. So again, that's an example of energy being transferred into your bones. And the last one then with the lowest wavelength and the highest frequency is actually gamma rays. So gamma rays a lot of the time are involved when you have a nuclear radiation. So if you're doing nuclear fission or fusion in a nuclear reactor, you'll emit a lot of gamma rays which will carry that energy. Okay, let's move on to the questions. Alright, a few questions for you guys. Feel free to pause the video and have a go. Okay, so question 1, we ask calculate the wavelength of the electromagnetic wave with a frequency of 2.3 times 10 to the 9 hertz. So for this question, essentially what we want to do is we want to be able to use the wave equation. So remember, the wave equation applies to electromagnetic waves, and we know for EM waves, the speed is always going to be equal to 3 times 10 to the 8 meters per second in a vacuum. So if we have the wave speed and we have the wave frequency, then we can just rearrange for the wavelength. So this is 2.3 times 10 to the 9 hertz and multiplied by lambda, which we don't know. So we can rearrange for our lambda, and therefore our wavelength is going to be 3 times 10 to the 8 meters per second over 2.3 times 10 to the 9 hertz. And if you put that into your calculator, you should get approximately 0.13 meters. Okay, so hopefully you got that one right. Next question then, question 2, which of the below waves has a higher frequency than microwaves? So we've got ultraviolet, radio and infrared. So which of these has a higher frequency than microwaves? So let's look on our chart over here. So microwaves all the way on this side. So anything, and we can see over here we've got lower frequency, over here we've got a higher frequency. So anything past this point for microwaves will have a higher frequency than it. So you can see ultraviolet is past that point. It's over here. Radio waves are to the left of microwaves, so don't have a higher frequency. Infrared is also to the right of microwaves on this side, so it does have a higher frequency. Okay, so the answer would essentially be both ultraviolet and infrared, but not radio waves. Question 3, which of the below waves has a longer wavelength than X-rays? So again, let's consult our chart. So X-rays are over here, and we'll use a different color just to make it clear. X-rays are over here, and we're looking for waves which have a longer wavelength. So let's take visible light. Visible light is to the left of the X-rays, and towards the left you can see you do have a longer wavelength. So visible light would be 1, so we can pick that. Gamma rays you can see is to the right, and that is the ones with a lower wavelength, so we wouldn't tick that. And the last one is ultraviolet, and ultraviolet is also to the left of X-rays, and so this one would also be correct. Okay, so for question 3 you should have got visible light and ultraviolet. That's it for the questions, and hopefully you got those ones correct.